but there's not too much to it. So this is just some more, I guess, terminology, so to say. This is actually what I said before, that the A here in the ordered pair AB, we call it the X coordinate. Some people call it the first coordinate. I think the book might actually do that, but I don't remember for sure. B, we call that the Y coordinate, or the second coordinate, some people call it. I think actually I might be wrong about this terminology. I've seen some people call the X coordinate the abscissa and the Y coordinate the ordinate. I could be wrong about that, but this is fine what we have. Here, I'm just saying what it means for 2 points to be equal. Essentially, all I'm saying here is that they're equal exactly when their coordinates are the same. So their X coordinates are the same and their Y coordinates are the same. So I guess you can also think of it visually, as I have here as well, that two ordered pairs are the same exactly when they coincide as plotted points in the Cartesian plane. You know, if you were to plot them in the plane and they overlap each other, you know, they're exactly the same point, they coincide, then they're the same. But in particular, you should notice, that's what I'm trying to say over here, order does matter. I'm not sure if I said this earlier, but with a set, like a solution set of of an equation, order does not matter in a set. Here, order does matter, okay? Order does matter. Sorry, I forgot to put my phone on silent. But order does matter. So 2, 3, and 3, 2 are not the same. I mean, even if you went to plot them in the plane, right, they would not overlap each other. So it's just something I wanted to point out. A lot of the stuff you might have seen before, but if you haven't, that's okay, though. It's just, you know, I've done this example with students in the past, but I figured, what the heck, let's go through it now. So if we were to plot again, -3, 0, right? You start at the origin, right? You're going to move. You always start at the origin. You locate -3 on the x-axis, which is the same as moving to the left 3 units. Now, since the y coordinate is 0, you're not going to move up or down at all. You stay on the x-axis, which is the horizontal axis. Unless otherwise stated, the horizontal axis is the x-axis. The vertical axis is the y-axis. I actually have seen cases where they were switched, but not in this class. I tilted this a bit to make it easier to see. Hopefully it works. So for 2, -1, okay? For 2, -1, right? Again, we start at the origin. You always start at the origin. I don't think I said that before. You go to the right 2 units. That is, you locate 2 on the x-axis. Here you're going to go down 1 unit because the y-coordinate's negative. And finally, for -1, -1, right, you're going to go to the left 1 unit. You locate -1 on the x-axis. You go down a unit because the y-coordinate is negative. I mean, hopefully that's not too terrible. So okay. Now we get to something really cool, the distance formula. In other words, we're going to be able to determine how far apart 2 points are in the plane, in the xy plane. And basically, again, it's just by this formula. So if you have 2 points P and Q, like so, the distance between them in the Cartesian plane is this. You subtract the x coordinates, You use one x coordinate from the other, square that difference. You subtract one y coordinate from the other, square that difference. You add the two, and then take the square root. You add the squares, right, with squaring, and then you take the square root. What's nice about this is I know normally with subtraction, order matters. However, here, since you're squaring, order is not going to matter. I mean, here from the formula, you'll see probably on, I think it's on the next slide, you'll see, if I'm subtracting the x coordinate of point Q from the x coordinate of point P, but if I did the other way instead, it's not going to make a difference. Because again, we're squaring. So that's what's happening here. And same thing with the y coordinates. I mean, I did plot P and Q as if they look like this, but of course that doesn't have to be the case. Let me illustrate what I'm trying to say with an example. P and Q could be the same. In that case, the distance would be 0. So for instance, let's find the distance between points 1, 4 and 2, 7. Okay, so again, I'm going to say P is the first point. I'm going to let Q be the second point. So what do? We subtract. We have the x coordinates here. So if you want to, so what we do then is we subtract one x coordinate from the other one. So here I'm doing 1 minus 2. Then I'm squaring that. For the y coordinate, same thing. We have 4 minus 7. 4 minus 7 squared. So we have -1 squared plus -3 squared, right? And then we take the square root of that sum. So this is 1 plus 9, and we get the square root of 10. So the distance between these 2 points in the plane is equals the square root of 10. And what I'm trying to show you here is if I am using the formula, but if I took P to be 2, 7 and Q to be 1, 4, and I went right by the formula, again, it's not going to make a difference, right? Here, for instance, I subtracted one x coordinate from the other, right? I did 1 minus 2. Here, instead, I'm doing 2 minus 1. Here, I'm subtracting one y coordinate from the other one. The y coordinate of one point from point, that's better. 7 minus 4. Here, it's 4 minus 7. But again, it's not going to make a difference because we're squaring. So we have 1 squared plus 3 squared, which again is 1 plus 9. And we take the square root of that, which is the square root of 10. So it doesn't matter, actually. Let me say this also. I forgot to say this. The distance graphically, or I guess geometrically, it's the length of the line segment whose endpoint in the plane, whose endpoints are P and Q. It's actually equal to the length of this line segment. So I just redrew it here. I know I redrew the orientation a little bit differently, mostly because I want to kind of sketch a proof of this, of why the formula is true. It's really just Pythagorean theorem. The idea is, as you can see here, hopefully, if you have that line segment P to Q, right? Sorry to go back and forth like this. The idea is you can form a right triangle where the hypotenuse, which is the side, the longest side, the side opposite the 90-degree angle, is this line segment. Now, how do we do that? Well, that's what the next slide shows. The whole idea is you can draw these dashed lines in. I mean, I drew some more dashed lines than necessary, so hopefully everyone can see what's happening. But we have this dashed line from P outward, okay? Not sure why this y sub 1 is here. That, I think, is a mistake. Let me just, unless there's something I'm overlooking, but I don't think there is. Let me just cross that out. And we draw our dashed line from Q down to the x-axis. But hopefully you can see that this point here has coordinates x sub 2, because it's directly under Q, and y sub 1. The whole idea is you start at the origin, you go, and now you're under Q, okay, directly under, so the x-coordinate's the same. You're only going as high as p, and height, how high you are above or below the x-axis, that's what the y-coordinate is. You're just going as high as p, so the y-coordinate's the same. But basically what's going to happen is, if I clean this up a bit, we get something that looks like this right triangle here. Okay. All right, let me just erase that other thing because, let me just erase this. Okay. What happened was I probably forgot to erase these numbers here, and they're still over here. But anyway, what we get altogether, what I'm trying to show you, I mean, the textbook, I think, has better pictures. I think they do the proof as well. You're going to get this right triangle where the length of this side here, the height, is y sub 2 minus y sub 1, the difference in y coordinates. And the length of this leg here is just the difference in x coordinates, as you can see. So how do we get the length of the hypotenuse? Well, it's a right triangle, so we use this famous theorem, Pythagoras' theorem. Excuse me, the Pythagorean theorem. And that's what it boils down to. That's all. So it's no fancy trick or something. It's just Pythagorean's theorem. That's all it's based on. Okay. So again, the textbook, I'm sure, has better pictures. I drew what I could, so to say. But that's okay. I'm not going to expect anyone to prove this on the test. Not to say you're not capable, but I just think it's better to be able to use the formula. Okay. Let me now get to the recording.